Okay, so I want to start off by kind of talk about the big idea process between last semester versus this semester, and that's going to kind of help guide um, our the problems that we're going to do and the steps that we're going to take. So first semester, I'm going to put some of these notes up here. First semester, we started our calculus topics with derivatives. Okay. And derivatives is just a fancy word for what? Slope, right? Rate of change, right? And slope is just change in y over change in x. Right, so if we were looking at the graph, what we're able to do, we're able to pinpoint any point on the curve and figure out the rate of change at a specific point on that curve. It's not just an approximation, it's the exact rate of change at that point. Okay. Now this semester, we're going to be undoing our process, and that process is going to be called antiderivatives. Okay, so all the derivatives that we found, that we're going to be able to learn how to work backwards, back up to our starting point. But something more than that, application-wise, we're going to be able to do something that is the opposite procedure of this slope that we understand, because the main operation that is applied in finding slope is what? The main operation here is division, right? So division, rate of change is division. So how do we undo division? Multiplication, right? So think about multiplication here. Imagine rather than dividing y2 minus y1 by x2 minus x1, if we do multiplication, which is undoing this process that we have here, then we have y2 minus y1 times x2 minus x1, or we can say x2 minus x1 times y2 minus y1. So what does that mean visually? Well, x2 minus x1 is just going to be some horizontal distance between 2 points, right? y2 minus y1 is just going to be some vertical distance between 2 points. So what do we get if we were to multiply these two lengths together? Area of what? Area of, what's the shape here? Rectangle, right? Area of a rectangle. So we see that the inverse process of slope is going to be something that produces length times width, which is area. And that is going to help us guide what we're going to do with this unit here. The application is that if we take the antiderivative, we are also finding an area related information about a region. So we may have a region that is not a rectangle, right? However, we can think of it as adding infinitely thin rectangles from one end to the other. And if we do that, then we're going to be able to achieve the actual area under the curve. So we're going to bring back this concept of limits, but we're going to explore that more tomorrow. So today, we're just going to be exploring how to find an approximated area of a region. But that's why we're so focused on this idea of rectangles, is because if I multiply x2 minus x1 times y2 minus y1, we do get something that is area related from a rectangle's perspective. Okay, so today is all about approximation, and these rectangles that we're going to use to approximate the area under the curve is called Riemann sums. Okay? And there's different ways that we can draw rectangles to produce approximations. And depending on how we draw the rectangles and how many that we draw, that's going to also influence the accuracy of these rectangles. Okay, now we're never going to have to worry about we don't, at least in this course, we don't have to worry about how accurate our approximations are. We just have to be able to produce the approximations that the problem is asking for us to find. Okay, just depending on what type of rectangles the problem is specifying. Now, let's consider this function. Okay, x squared plus 1. That's just the parabola here between -2 and 2. So below the curve, above the x-axis, and between these two endpoints, we see that this is a region that is not a specific shape, but it doesn't matter. We're still going to take this region and we're going to approximate the area of this region. Okay, suppose we want to estimate the area of the shaded region using a given number of rectangles. Okay, so again, the big idea here is approximation. Okay, it's not going to be an exact exact value of this shaded region's area. That we'll explore tomorrow. Okay, so today we're just going to be talking about how do we create these estimations that the problem is asking for us to find. So the first type of approximation is creating upper rectangles or circumscribed rectangles. Okay, so if you look at these rectangles here, if I were to add up the areas of these rectangles, will it be lower or higher than this area? Higher, right? We see all these rectangles produce regions that's peaking above the curve. So this is obviously going to produce an area that is greater than this. Okay? We don't have to worry about how much greater it is. We just know that it's greater. Okay. So we know that these rectangles will provide an overestimation of the actual area under the curve. Okay. So let's talk about how we create these upper rectangles. So I'm gonna indicate these rectangles that we see in front of us. I'll call this rectangle 1, rectangle 2, rectangle 3, and rectangle 4. Okay, and just for purposes where we can just have a more concrete values to talk about, let's say all these increments are by 1. So let's say this is -2. This is the x-intercept here is -1. Let's say this is 0. X-intercept of 1, x-intercept of 2. Now, the way that we create these upper rectangles, or ensure that every rectangle is going to sit above the curve, or at least portions of it above the curve, we're going to look at each subinterval, and we're going to look at the height of each subinterval towards the curve. Okay. Now, if I extend -2 to the curve versus -1 to the curve, which one is going to produce a higher y value? -2. Okay, so between the two endpoints, we're going to choose the higher of the two boundaries. You see the -2 is going to extend to a higher point, so you're going to highlight that point, and that point is going to represent the height of that first rectangle. So you're going to drag that height over the entirety of the subinterval, and that's how we can ensure that we can create rectangles that's going to sit above the curve. Okay. Now, let's look at the second subinterval here. Which height is going to be higher versus to the curve, -1 or 0? -1. -1 is hitting a higher y value on the curve than 0 is. So we're going to extend to that height, highlight that point, drag it over. That way we can ensure that we can create a second rectangle in that second subinterval that is going to produce an area more than higher than the curve. Now, the third region here, which height is hitting the curve at a higher point? At 1, yep. So wherever that y value is, if we extend to the curve, because of the way that the curve is changing, it's not always going to stay as the left endpoint, right? Here it's going to actually be the right endpoint because the curve changes direction. So we see between these 2 points, the graph at 1 is hitting at a higher y value. So you're going to take that. That's going to be your guide. Extend the graph over, and that's going to represent the height of your third rectangle. And finally, your fourth rectangle, which is hitting a higher point at 1 or at 2. At 2. So you're going to highlight that point, drag that over. That's going to represent the height of your fourth rectangle. So now we can ensure that every one of these rectangles is going to produce a slight over approximation. So therefore, if we add up the areas of all 4 rectangles, it will guarantee to be higher than the actual area of my curve. Okay, notice that one corner of each rectangle is on the graph. This ensures that the height of the rectangle is the same as the value of the function at the point where they connect. So it's important that we extend, that we use the curve to represent the height of every rectangle that we want to create. Okay, so now let's talk about the same region, but now we want to guarantee an under approximation. We call this lower or inscribed rectangles rather than upper or circumscribed rectangles. Okay, again, I'll name each of these rectangles 1, 2, 3, and 4. And again, we'll make it easy, make it all go increments of 1. Okay, so now same process, but now we want to purposely choose the lower of the 2 heights. So which is hitting, extending to the graph at a lower point, -2 or at 1. -1, right? -1 is lower than up here at -2. So we want to choose the height at -1, extend over that first subinterval. And that way we can ensure that this area is going to guarantee to be less than the area of this region here. Right. Okay. Same idea here between -1 and 0, which is hitting the graph at a lower point. 0. Okay. So take 0, extend over the second subinterval, let that be the height. And then between 0 and 1, which is hitting at a lower point. At 0. So this looks like the third rectangle is also going to share the same height as the second rectangle, but we're going to let that represent the third rectangle because it's the lower of the 2 heights at 0 versus 1. And between 1 and 2, we see 2 is higher than 1. We want to choose the lower one. Now we can ensure that every rectangle that we draw is clearly below the curve. And if there's a gap, the gap is existing below the curve and not above the curve. So if I were to add up the areas of these 4 rectangles, we're guaranteed to have a value that is lower than the actual area. So we haven't learned how to find the actual area yet. Okay, we'll do that tomorrow and talk about a more efficient way to do it next week or a week after. But right now we're just focused on the approximation. Okay, any questions so far? Okay, now these are important concepts, but what's more important or what's more common is when a problem is going to ask you just for left-handed rectangles or just for right-handed rectangles. And left-handed rectangles, we don't really care about whether it's an over approximation or under approximation. We just want to find some approximation, and we want to find it quickly. So if the problem asks you for left-handed rectangles, then you're purposely just going to attach the left corner of each rectangle to the graph. So every left corner is going to guide the height of each subinterval. Some are above, some are below, but if it's asking for left-handed rectangles, the focus is not under approximation or over approximation. It just wants you to find the heights from the left side of each subinterval. Likewise, right-handed rectangles doesn't really care about whether the rectangles are above or below the curve. It just wants to ask to use the right endpoint of each subinterval to represent the height of that subinterval. And notice that we are purposely attaching the corners to the curve because we want the curve to represent the height of each subinterval. Okay, any questions with that? Okay, good. Let's go to the next page. Okay, so now we're going to start from scratch, and we're going to actually find the upper and lower sums just given the region, and we're going to have to build the width and build the subinterval and find each of the heights. Okay. So let's say the problem says use 4 rectangles to estimate the upper and lower sums, or find the upper and lower approximations for the area bounded by x equals 0. So x equals 0 is the y-axis. Y equals 0 is the x-axis. X equals 2 is this vertical line here, and the curve y equals x squared plus 1. So it's going to be this little region here in the first quadrant. Determine so the first thing that we need to do, and I drew a more extent or a larger version of that region here. Okay, and we're going to use this to kind of help us out. First thing we need to do is we want to determine the width of each rectangle. Okay, it says use 4 rectangles, so we want to create 4 equal subintervals. So to do that, our formula is b minus a over n. Okay, your a is going to be your left endpoint, your b is going to be your right endpoint, and n is going to be the number of subintervals that we want to divide into. So we see that this region extends from 0 to 2. That's your a and b value. And then your n is going to be what? 4, yeah, 4 subintervals. Okay. So let's go ahead and find our width that we want to use. My a and b values are going to be my left and right endpoint, 0 and 2. So 2 minus 0 over 4. What is that going to be equal to? 1/2. So my width is going to be 1/2. Okay. So we're going to increment by 1/2 from 0 to 2. So if I add 1/2 to 0, I get 1/2. If I add 1/2 to 1/2, I get 1 plus 1/2, 3/2 plus 1/2, 2. We should end up at our destination. Okay. If we didn't, then either we got the width wrong or we added wrong. Okay. So this is my first rectangle, second rectangle, third, and fourth. Well, first region, second region, third, and fourth region. Now we want to first start off by finding the upper sum. So that means with each subinterval, we want to look at where these vertical lines are touching the curve, and we want to choose the higher of the 2 heights. So between 0 and 1/2, which is hitting the graph at a higher point? 1/2. So you're going to highlight 1/2, and you're going to drag that height across your first subinterval. That is going to represent the height of your first rectangle, because we're purposely forcing our rectangles to be higher than the actual region, because we want an over approximation. Okay, what about the second interval? 1/2 or 1? Which is higher? 1, okay. Now, do you see a consistent C between each of these subintervals? We're always choosing the right one. Why is that? Because the curve is what? It's always increasing, right? So if the graph is always increasing, then the valley to the right is always going to be higher than the valley to the left. Okay. Now, we want to find the area of each of these rectangles. The formula for the area of a rectangle is width times height. what is the width of each of these subintervals? 1/2, right? Okay. So I'm going to say uppercase S of 4. This is just the notation to indicate that I want to find the area of these 4 rectangles, and these 4 rectangles will represent the upper sum, uppercase S. Okay. So every rectangle, we're going to build the area 1/2 times the height. The height is going to be determined for the first subinterval at 0 or 1/2. At 1/2. So we're going to say f of 1/2. We haven't found the height yet, but we know how we're going to find it. We're going to insert 1/2 into the function, and that function is going to give us the height, and then we're going to get that decimal value. But right now, I just want to set up myself for finding the area later. But this f of 1/2 is not a numeric value, but it does tell us how we're going to arrive at the height if we do the math a little bit later. Okay, second rectangle, width of 1/2. What's going to represent the height of my second rectangle? F of 1. Yep, f of 1 is going to be the height that I want to represent for my second rectangle. Third rectangle, also width times height, 1/2 times. Good, f of 3/2. Okay. And then finally, fourth rectangle, 1/2 times f of 2. Okay, I'm going to do the math for us and just skip the parts that's a little bit tedious. That's just finding the height of each of these values, right? So if my function is x squared plus 1, then f of 0.5 is just going to be 0.5 squared plus 1. Whatever that decimal value is going to be the height that I want for my first rectangle. Now, I want us to just see a different way of writing this out. What do you notice is common between each of these terms? They all share what? The same width, right? So technically, I could do this. I could just write the 1/2 once and then just add all of my heights, right? Same thing. It just makes it a little bit faster because we don't have to write 1/2 as many times because we know we're just going to distribute, or we can just find the heights and then multiply by 1/2 at the end. But this is the same thing, right? I just factor the 1/2 out. Here, if I just add up all the heights and multiply by 1/2, I can just save a little bit of time in terms of rather than having to multiply everything through by 1/2 every time. So I'm going to skip the tedious part here and just arrive at the heights. F of 1/2 is 1.25. The height of my second subinterval is going to be 2. Third subinterval is 3.25. Fourth subinterval is 5. Add that together, multiply by 1/2, and we get a region, an area of 5.75. Now, what is 5.75 in relation to the actual area? Greater. That's all we care about. Okay, it's a higher value. We don't really care how much higher it is. We do have different ways of improving approximation, but we don't have to know how accurate our approximation is. Okay, that's not something that we have to worry about in this course. Okay. So part B, we want to use the same region, same function, same formula, but we now are going to force an under approximation. Same subinterval. But now between each subinterval, we're going to choose what? The lower one, right? So between 0 and 1/2, we see 0 is going to hit the graph at a lower height. Between 1/2 and 1, we see that 1/2 is going to hit a lower height. Between 1 and 3/2, it's going to be 1, f of 1, and then between 3/2 and 2. So we want to ensure that every rectangle is sitting cleanly below the curve so we can guarantee that our approximation is going to be less. So whatever we get out of these area, it should be what compared to 5.75? Less, right? Should be less. Okay. So I'm going to use lowercase s of 4 to represent that this is going to be a under approximation. Same idea here. The width of every rectangle is also going to be what? 1/2. I could just factor that out. My first rectangle is f of 0. Thank you. Because we're choosing the left endpoint of each subinterval, right? Second rectangle, we're going to use f of 1/2 to represent the height. Third rectangle, we'll use f of 1. Fourth rectangle, we'll use f of 3/2. Notice that really the only difference between these two formulas is what? This one uses f of 2, but this one uses f of 0, right? So really a lot of shared information. It's just each of these heights represent a different height of a different rectangle. Okay, so I'm going to skip all the math here. F of 0, if we were to plug 0 into the function, I would just get 1. We already have f of 1/2, which is 1.25. F of 1 is 2. F of 1.5 is 3.25. The lower sum is going to end up being 3.75. So we can safely say, if this is the upper sum and this is the lower sum, where would you expect the actual sum to be, the actual area to be? Okay, it's going to be somewhere between. It's not going to be exactly in between, okay, because we have a better way of, but that's maybe a good guess, right? Somewhere between, if I find the average of these two, it's probably pretty close, but we can't guarantee that's the exact area. But we do know, at least based off of our limited knowledge, that at least we can conclude that our actual area is going to be somewhere between these two values. And a good guess would be halfway between. Okay. Okay, so there's one more type of approximation that we need to talk about today, and then we'll look at some practice problems from your textbook. Okay, so next page. Now there's also this midpoint rule here. It's similar to upper and lower sum, but now we want to use the midpoint of each subinterval to calculate the rectangle's height. So let's say I had this graph. Okay. And I worked out some of it already. This is the graph of 8 over x squared plus 1. We want to go from 2 to 6. We want to create our subinterval of 4 subintervals. And we use the same width formula as we do with other rectangles, b minus a over n. My a is 2, my b is 6. 6 minus 2 over 4. 4 over 4 is 1. So we're going to go from 2 to 6. So we're going to purposely choose the midpoint to extend to the curve and let that height represent the heights of each subinterval. So what's between 2 and 3? What's the midpoint between 2 and 3? 2.5. Okay, so I'm going to take 2.5, extend 2.5 to the graph, and let that height represent the height across my first subinterval. Okay, we're going to do this for each of our subintervals. Now, what do you think about the accuracy of this process versus lower sum and upper sum? Right, it should be better, right? And it is, because now we can't guarantee that this is a lower or over or under approximation. That's beyond what we're able to do, but at least we know that it's a better approximation because every rectangle is going to have parts that's sitting above and below. So it should produce a better approximation than just upper sum or just lower sum. Okay. So at least I wanted you to be convinced of that looking at these rectangles. Okay, between 3 and 4, we have 3.5. So I'm going to take 3.5, extend to my curve, and let that represent the height of my second subinterval. Between 4 and 5, I'll choose 4.5. Between 5 and 6, I'll choose 5.5. So this is another picture of what this rectangle is doing, right? So if I want to now find the area of these 4 rectangles, again, this is not going to be exact area, but visually, hopefully we're convinced that this is on its own better than just upper sum or just lower sum. What's the area of each of these subintervals of these rectangles? What's the width? 1. Okay, so I can factor that 1 out. I can do, I mean, really, it's not going to change anything, right? Because it's just a 1. And I can just add the heights of each of my subinterval. What's going to represent the height of my first rectangle? F of what? Good. Make sure that you don't just say 2.5, right? We don't know the height yet, but we know how to get to it. We know if we insert 2.5 into the function and get that decimal value, that's going to produce the height, whatever that decimal is. Okay. Okay. What's going to represent the height of my second rectangle? Good. F of 3.5. Then next, F of 4.5, and then finally F of 5.5. Yep. Okay. Not so worried about the math. The rest is just plugging in the calculator, but I just want us to understand the process, right? The process is more important to me. If I want to find the actual heights, I can just insert into my function, get all these decimal values, add them together, multiply by 1, and that's going to give me a midpoint approximation. Okay, it's not exact, but it is better than just upper sum or just lower sum. Okay. Is anybody confused about what the F of 2.5 and F of 3.5, why they represent the height and how we can get to the actual height? Okay. Let's flip over to, I printed out a page from the textbook so that we can kind of do a little bit of practice. So page 7. Okay, the shading is a little grainy. Okay. But I copied the same diagram twice so that we don't have to overlap and make it look confusing. But it's meant, the problem in the book is meant to shade the region from 0 to 4. So we want to just approximate the area using lower sum. for the first diagram, and then for the second diagram, we'll create an upper sum, and we'll find the approximated area. Okay. So just like before, we see our 4 subintervals. You got region 1 here, region 2, region 3, and region 4. Okay. To create a lower sum, we're going to look at each subinterval, look at where they touch the graph, and we're going to choose the lower of the two. So between f of 0 and f of 1, which height do we want to choose? 0, right? F of 0 is hitting the graph at a lower height than f of 1. We want to purposely choose a lower sum. So highlight where this vertical line hits the graph, and you're going to drag that height over. That's going to represent the height of my first rectangle. Okay. Now in my second interval, I'm choosing between f of 1 and f of 2, which is hitting the graph at a lower point, f of 1 or f of 2. All right, f of 1 is here, f of 2 is here. We want to choose a lower height, so highlight that point, drag that over, and that's going to represent the height of my second rectangle. Okay. My third subinterval, which is hitting the graph at a lower point, f of 2 or f of 3. F of 2. And then between f of 3 and f of 4, which is hitting the graph at a lower point, f of 3. Okay. Highlight that point, drag that height over. So we'll do lowercase s sub 4. Every height of my rectangle is what? 1. I'm going to use function notation first, but then we can just read the graph and hit the find the height, right? F of 0 is the height of my first rectangle, plus f of 1, plus f of 2, plus f of 3. Okay, this is easy enough where we can just look at the graph and find the height. What's f of 0? What's that y value? 1. Okay, what's f of 1? 3. What's f of 2? 4. And to the best of our approximation, f of 3 looks like what? 4.5. That's good enough approximation. Is every rectangle safely sitting below the curve? Yes, that's a good sign, right? That means we drew the rectangles correctly. If there's a gap, the gap should be sitting between the curve and the rectangle. The rectangle should not be none of the rectangles should peak above the curve. Okay, I add all this up, I get 16.5. This is lower than the actual shaded region below the curve and between 0 and 4. Okay. What do you expect out of the upper sum? Should be greater than 16.5, right? We don't have to worry about how good these approximations are. We just have to be able to find them and understand what is represented. Oh, did I get the wrong? Sorry. I did the upper sum first on my I got these two mixed up on my key. Yep, you're right, 12.5. Thank you. 16.5 is going to be the upper sum. Okay, so again, each subinterval. First subinterval, I want to choose the higher of the two region, which is going to hit the point at a higher point. F of 1 or f of 0? F of 1. So highlight f of 1, drag that over the first subinterval. And now every rectangle that we draw should be clearly showing regions above the curve. Okay, f of 2. Oh, sorry, between 1 and 2, we choose f of 2 because it's hitting a higher point in that second subinterval. Drag that height over. That's the height of your second rectangle. Third rectangle, f of 3 is hitting the graph at a higher point. And then between f of 3 and f of 4 is hitting the graph at a higher point. Uppercase s of 4. The height is still, sorry, the width is still 1. But now we want to start at f of 1 because f of 1 is going to represent the height of my first rectangle. So f of 1 plus f of 2 plus f of 3 plus f of 4. Okay, so that's 1 plus 3 plus 4 plus 4.5. My bad, over here. 3 plus 4 plus 4.5 plus 5, it should be 16.5. Okay, let me just quickly do one where we have to use a function similar to the one that we did on the previous page. So let's say for y equals square root of x, we want to do the upper sum, okay? And this is extending from 0 to 1. First thing we do, this one is not drawn as nicely for us, so we have to find the width. The width is going to be b minus a over n. What's my a and b value for this shaded region? 0 and 1. And how many subintervals do you see? 4. Yeah. So it's going to be 1 minus 0 divided by 4. Okay. What's that going to give us? 1/4. So what you're going to do is you're going to keep adding 1/4 to each subinterval until you reach your destination on the right side, 1. So 0 plus 1/4 is 1/4. Plus 1/4 is what? 1/2. Plus 1/4 is 3/4. Plus 1/4 is 1. Okay, so you know you're on the right track if we can keep adding the width and arrive at your right endpoint without any mistakes. So I want to do the upper sum first. So I want to purposely choose the higher of the two subintervals between 0 and 1/4. Which is hitting the graph at a higher point? 1/4. So I'm going to highlight 1/4, extend that over, and that's going to be that's going to represent the height of my first rectangle. Okay. This is always increasing, so that's nice. We can just basically always choose the right endpoint and ensure that we're going to hit the higher of the two. Okay, so this is S, uppercase S of 4. Okay, width times height for every rectangle, but the width is all the same. Width is what? 1/4. I can just accumulate the sum of the heights. What's going to represent the height of my first rectangle? F of 1/4. Or I can say y of 1/4. Essentially, I'm just plugging 1/4 into the function, whatever that decimal value is, plus f of 1/2 plus f of 1 plus f of 3/2. Sorry, my bad. 1/4, 1/2, 3/4, and 1. Notice that we don't use f of 0 because f of 0 doesn't represent the height of my higher subinterval. Okay. So whatever all those decimal value gives us, that's going to be your upper sum. Okay, so just to kind of give you a preview as to how to approach these problems. After you draw your subinterval, you can extend to the higher of the two values, and you can work the problems out on this page. I have a lot of homework problems here between page 7 and page 8. And then the others I don't include, you can put on a separate sheet. All right, homework tonight. Check your homework page. Also find this on my website. Okay, come get your phones.
It's a restaurant.
Yep. Right.